Hello, I welcome you all to this another interesting screencast. The problem reads, draw the shear and moment diagrams for the beam. This problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. So we have a cantilever with three concentrated loads, 1 meter apart. So let's draw the free body diagram. At A, we expect AY, then AX, and then we have a moment MA. Okay, let's apply the equations of equilibrium. So we have summation of moments about point A equal to 0 and clockwise being our reference. Right, so what do we have? We have a 4 times 3, okay, plus 6 by 2 plus 8 by 1 plus MA equal to 0. Therefore, our MA is just going to be equal to 4 by 3 plus 6 by 2 plus 8. So this gives us a 20, right? 12 plus 4, 24 plus 8, 32. Then minus 32 kilonewtons meters. Right, and then summation of forces in the y equal to 0, going up as our reference. We have minus 4, minus 6, minus 8 plus ay equal to 0. Therefore, our ay is just going to be equal to minus plus 18, right? Of course, minus 4 minus 6 minus 8. And then summation of forces in the x direction equal to 0. What do we have? Of course, ax is just going to be equal to 0. So for the moment, minus is just a direction that is going to change. So there we go. So this moment, therefore, is supposed to be instead clockwise, which is a 32 kilonewtons meters. Ax, we said is just 0. Ay, we said is 18 kilonewtons. All right. So for this one, we have 3 intervals where we are supposed to do sections. Okay, if we wanted to do, say, to draw the shear diagram, so we are supposed to do section there, with section there, with section there. So this is too lengthy. Okay, instead of sectioning, we're just going to use the differential equations to draw the shear and the bending moment diagram. So we do know that, let me just draw a boundary here. Okay, we know that the rate of change of moment with respect to x is equal to shear, and therefore moment itself is just equal to the area under the shear load diagram. And the rate of change of shear with respect to x is just equal to the distributed load, and where the shear itself is equal to just the area under the load or the distributed load diagram. So these are the two differential equations that we're going to use to do to plot our equation, right? So let's do that. Let's do that for now. Okay, let me draw our reference lines like so. I think I draw another one like so. Great. So what do we have there? We have the shear force diagram. and we have the bending moment diagram. This is positive, minus, positive, minus. Right. So what do we have at this point? We've got shear. We've got shear at this end. Let's call this end as B. Okay. So I move this a little bit up. Just want to move this just a little bit up, maybe up to there. Great. So we have shear at B, F4. Let's say 4 is coming up to there to just save space. So let's write this as 4 kilonewtons minus. Then from B, let's say this is CD. From B to C, we know that Q, which is the distributed load, is equal to 0. Therefore, we expect the slope of our shear diagram to also be equal to 0. Okay, so 0 slope is just going to be a straight line like that. That is from B to C. Okay, like this. And then when we reach where we have a concentrated load of 6, then these are going to interact algebraically, and both of them are negative, so we have a minus 4 minus 6, which gives us a minus 10. So this is going to shift to go down to 10. Let's imagine maybe 10 is somewhere there. Okay, so let's say this is our 10 kilonewtons. And then this from C to D, Q again is equal to 0. There is no distributed force there, therefore our slope is also going to be 0. So we'll have a straight line like this. Then when we reach D, 10 again is going to interact. 10 is going to interact. Maybe this has become too long for me. It is consuming space. Let me just reduce it. I'll bring it here. So this was a 10. So when we reach D, 10 is going to interact with 8. So both of them are negative. So minus 10 minus 8, which gives us minus 18. So we expect a movement, a downward movement, maybe up to somewhere there. Okay. And this is equal to up to somewhere there. Okay, sorry, I want this line to be straight. Okay, something like that. So we are saying this is minus 18 kilonewtons, right. And then between D and A, again, Q is equal to 0, therefore the slope of the shear will be 0. So we expect again a straight line or a 0 slope. Then when we reach this point here where we have A, we have another support reaction of AY, which is 18. So we have the two now interacting. A minus 18 plus 18 equal to 0. So this is the point where the business has to be closed. Closure of our business. Alright. So this is also 18 kilonewtons. And all this is negative. Great. So this is the diagram for our shear. Great. So we are done with the diagram for our shear. We need now to draw a diagram for moment. Okay. So of course positive minus. Great. So let's do that. Let me just lift this. I take it somewhere here much closer to maximize on space, because space now has become a little bit limited. Great. So let's wrap this. So let's look now at slope, at shear. From B to C, our shear is negative and it is constant. Okay, negative value of 4. So we expect the slope of our moment to also be negative and constant. Okay? Yeah. So at B, of course, we don't have any boundary, any moment, applied moment to a couple. So we expect moment to be 0 at B, and then it will have a negative gradient, which is constant. Right, let's draw it. And what's its magnitude? Its magnitude is this moment. We know is magnitude of moment is just area under the shear diagram. Area under the shear diagram. And our shear diagram is just rectangular, so it's just a 4 times the length 1, which is just equal to 4. Okay, so our slope there, our slope we said is constant, so let's draw it at negative, so up to somewhere there, up to there. Okay, it has to tarry where C is, somewhere there. All right. What is this value? We said this value is 4 kilonewton meters. This is 4 kilonewton meters. Great. And then from C to D, our shear is negative again and constant. Therefore, we expect moment to be negative, the slope of moment to be negative again and constant. And this magnitude is just going to be equal to 10 times 1. 10 times 1, which just gives us 10. Okay, it gives us a 10. Okay, so mind you, we are starting from 4, so the 2 will interact, and these are all negatives. Okay, these are all negatives, so we'll have a minus 10, okay, minus 4 equal to minus 14. All right, these will interact. All right, great. So from here the slope is going to, we are going to move from there again. That will be another slope. All right, something like that. Let me rub this black dot. All right, great. Okay, there we go, up to say here. Okay, and this point is this point we said is 14. Okay, this is 14. This is 14 kilonewton meters. Let me write it the other side. 14 kilonewton meters. All right, and then finally from D to A, the shear is negative and constant. The slope also be negative and constant for moment. So let's just find the magnitude. Let's find the magnitude. So we have 18 minus, these are minuses, by 1, which is equal to just minus 18. So we are coming from a point where moment is minus 14, so it will be minus 14 minus 18. This gives us, it's a 32, right? Yes, so minus 32. So move again from here, So let me just reduce the slope a little bit for this because I don't have space. Sorry, let me redraw them. I don't have space, I just make them a little bit. Let 4 come maybe something like this. So like this. This was our 4 kilonewton meters. And then let our 14 maybe come up to somewhere there like this. So that was our 14. This was our 14. And then finally we have 32 somewhere there. Okay, this is 32 kilonewtons meter, right? And then later on at the very end there, we have a moment at this end. The reaction moment, of course, is clockwise. But if you are to make a section just before this clockwise moment, you find we are going to have the counterclockwise, which is positive. Okay, and that is the one that is going to sum up with this minus 2 plus 32, the counterclockwise, which gives us a 0, and hence a closure. Okay, hence a closure, like so. Great. Okay, and of course we said this is negative, so we are saying the equation that governs the shear function, these are polynomials of degree 0, and the equation that governs the moment, they are polynomials of degree 1. These are linear functions. So we have a linear increase from B to C for moment, linear increase from C to D, and a linear increase from D to A. Alright, so I think this is about it, and I hope the video was helpful. If it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and see you in my next screencast.